Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be solving a question on recursive sequences, and the question reads: a sequence x of n is defined recursively by x1 equal to 2 and xn plus 1 equal to half into xn plus 2 over xn for all n in the set of natural numbers. We have three equations. First, we need to show that for all n in the set of natural numbers, x of n is bounded between the square root of 2 and 2. B says we should show that x of n is decreasing, and D says we should study the convergence of x of n. So here we are going to deduce its convergence, and then we state the limit. Alright, so without wasting much of your time, let's get started with the solution. So for my analysis of this question, I introduced a function into this question. Alright, and I proved the first part of the equation by mathematical induction. So by mathematical induction, I let P of n be the statement. I let P of n be the statement. What I am proving that for all natural numbers, x of n is bounded between these two numbers. For all n in the set of natural numbers, this is what I'm proving. Now, to prove by induction, the first thing to do is that we have to verify that. We call that the base case. The base case where we verify that the statement is true for the first value of n. So the first value of n is 1, so we need to verify that p1 is true. But our p1 is simply the statement root 2 is less than or equal to x1 less than or equal to 2. But since we were given x1 as 2, then that the inequality holds, right? Because root 2 is normally less than or equal to 2, and 2 itself is less than or equal to 2. We know that 2 is not less than 2, but since 2 is equal to 2, right, when we are dealing with the disjunction or for P or Q to be true, either of them must be true. We know that 2 is equal to 2. That statement is true. 2 less than 2, the statement is false. So if we combine it using OR, we are going to have 2 is less than or equal to 2. Since 1 is already true, we don't need to bother about the truth value of the other one. So here we just need to say since the square root of 2 is less than or equal to 2 itself, which is also less than or equal to 2. Now I am going to replace the 2 at the center with x1. So I get the square root of 2 is less than or equal to x1 less than or equal to 2. So p1 is true. So the statement p1 is true. Since p1 is simply the statement root 2 is less than x1 less than 2. Now the next thing is what we call the induction hypothesis. Sorry for the bad spelling. The induction hypothesis. Now here we have to assume that the statement is true for a certain value of n, which is we take n equal to k. So we assume that P of k is true. So what does this mean? This means that root 2 is less than or equal to x of k less than or equal to 2. That's the assumption. Then the next step is what we call the induction step, where we now prove that the statement P of k plus 1 is true using the fact that P of k is true. So we prove that P of k plus 1 is true. That is, what do we need to prove? We need to prove that the square root of 2 is less than or equal to x of k plus 1 less than or equal to 2. That's what we need to prove. So let me try to put it in the bold coloration. Okay, so like I said, I introduced a function. Alright, so let me start my analysis. So I realized that the sequence x of n plus 1 is defined in terms of x of n recursively, and I clearly see that I could also say, okay, my f of x is the function half into x plus 2 divided by x. So my x of n plus 1 will just give me f of x of n. This is what I'm saying. If I pose my f of x, the function, to be equal to half into x plus 2 divided by x, right? It therefore means that 2 divided by x, it therefore means that if I want to look for f of x of n, I'm just going to get half into x of n plus 2 divided by x of n. All right, and this is equal to what? X of n plus 1. It was defined to us ever since. So we have created a relationship between the function we have found, or the function we are using, and the n plus 1 term of the sequence. So we have that the n plus 1 term of the sequence is f of the x term of the sequence. Now I'm going to tell you why I did this. Okay, so from here, what do? I now need to study the monotony of this function. Alright, I need to know if the function is increasing or the function is decreasing. So for us to know it, we must take the derivative of the function and we look for the sign of the derivative. If the sign is positive, the function is increasing. If the sign is negative, the function is decreasing. If in fact there must be a sign. So f of x, let's come back to this. Our f of x is half into x plus 2 divided by x. I'm going to write it as 2x to the power negative 1 so that I can easily differentiate, and you see. So how will I do to get f prime of x? Right, I keep the half outside. When I differentiate x, I get 1. Alright, when I differentiate 2x to the negative 1, I need to drop down the negative 1. It multiplies with 2. Then I take x to the power negative 1 minus 1, which is just negative 2, and we can negative 2, right? So we can rewrite this as half into 1 minus 2 divided by x squared. Okay, so if we simplify by finding the LCM is x squared. The numerator will give us x squared minus 2. So this is clearly the derivative of the function. Now we need to look for the sign of the derivative. You realize that your x squared in the denominator is always positive no matter the interval of x. But what is in the numerator? We don't know the sign, right? Because x squared minus 2 could be positive or could be negative. For example, if I take x to be 5, 5 squared minus 2 will be positive. But if I take x to be 1, 1 squared minus 2 will be negative. So which interval of x are we going to use? We are now going to come back to the induction hypothesis, which is saying that our x of k is between root 2 and 2. Okay, so we are going to use this induction hypothesis 2 times. We are going to use it to first of all get this interval, because we assume that for any value of x being x1, x2, x3, x4, x5 until xk, that value of x will always lie between root 2 and 2. So we say, since we have the square root of 2, less than or equal to x less than or equal to 2, it therefore means that, in fact, if we just concentrate on this part, you realize that we can square both sides and we are going to have 2 is less than or equal to x squared. Now we can subtract 2 on both sides and we get 0 is less than or equal to x squared minus 2. And if 0 is less than or equal to x squared minus 2, it means x squared minus 2 is greater or equal to 0. That is positive. So you now realize that since our x squared in the denominator is always positive and the numerator has been proven to be positive, so the ratio of two positive functions is positive. When you multiply it with a positive number, it is positive. So we can conclude that hence our f prime of x is always positive. Alright, so if f prime of x is always positive, then what do we have? F is increasing, right? Because the sign of its first derivative is positive. That's f prime of x is greater than 0. Now, since f is increasing, now let's go back to the induction hypothesis. The induction hypothesis says that our x of k is between root 2 and 2, right? Now I'm going to take the function, I'm going to take f all through. So I'm going to have f of root 2 less than or equal to f of x of k less than or equal to f of 2. Now I'm going to write down why this inequality holds, because f is increasing. If f was decreasing, we are going to switch the bounds of the inequality. It means that rather we are going to begin with f of 2 and then we end with f of root 2. But since f is an increasing function, then the inequality signs remain unchanged. Alright, so from here, that was why we are finding the monotony of f to know if it is increasing or decreasing. Now from here, you realize that your f of k is simply your f of x of k is simply x of k plus 1, because we have that x of n plus 1 is f of x of n. It means that x of k plus 1 is f of x of k. Alright, that's another reason why we were taking f all through. So it therefore means that what is f of root 2? I just need to come to f of x and I replace x with root 2. So it's going to give me half into, I need to put x with root 2, then plus 2 divided by root 2. That's what I have in my lower bound, less than or equal to. Now my f of x of k is simply x of k plus 1, and then my f of 2 is simply replacing x with 2. So this is what we have. Alright, so let us try to simplify the bounds. Okay, so we have half into root 2 plus, now 2 divided by root 2 is 2. Now 1 divided by root 2 is the same as root 2 divided by 2. So I was just trying to simplify. Okay, less than or equal to x of k plus 1, less than or equal to half into 2 plus 1. Alright, so what does this mean? It means that if we simplify, you realize that 2 cancels with 2, and root 2 plus root 2 is 2 root 2, but when you multiply with half, so you have something like half into 2 root 2 less than or equal to x of k plus 1 less than or equal to, this is simply 1.5. Okay, that's 3 divided by 2. I know why I'm writing 1.5. Alright, so this therefore means that the lower bound here stays as the square root of 2 less than or equal to x of k plus 1 less than or equal to 1.5. But what did we need to prove? We needed to prove that your x of k plus 1 is between root 2 and 2. But we have proven that x of k plus 1 is between root 2 and 1.5. But now there's a transitivity property, right? There's a transitivity property. We know that 1.5 is normally less than or equal to 2. That one is true. We know that 1.5 is less than 2, correct? But 1.5 is not equal to 2. So the sentence or the statement 1.5 is less than 2 is correct. The statement 1.5 is equal to 2 is false. But when we are linking the two together, that is, we are taking 1.5 less than or equal to 2, the resulting statement is going to be true, because the logical connective involved is the disjunction. And for P or Q to be true, either statements, if we have at least one statement being true, then the result is going to be true. So since 1.5 is less than or equal to 2, okay, since 1.5 is less than or equal to 2, and or let me write it this way, x is less than x of k plus 1, x of k plus 1 is less than or equal to 1.5, and the 1.5 itself is less than or equal to 2. Now we need to deduce. So we deduce that by the transitivity property, our x of k plus 1 will also be less than or equal to 2, because x of k plus 1 is less than 1.5. Then clearly 1.5 is less than 2. So anything that is less than 1.5 is automatically less than 2. Alright, so we can now conclude that the proof is out, that is the square root of 2 is less than or equal to x of k plus 1 less than or equal to 2. So we have succeeded in resolving the first part of the equation, that is proven by mathematical induction. Alright, now the second part is saying that we should show that x of n is decreasing. So we are going to define what a decreasing sequence is. So we are showing that x of n is decreasing. So x of n is decreasing if and only if, so it's a double implication, if and only if x of n plus 1 minus x of n is always less than or equal to 0. So if we are able to look for x of n plus 1 minus x of n, and then we find a sign, and then we show that the sign is negative, then we have shown that x of n is decreasing. So let us begin. X of n plus 1 itself minus x of n is equal to, x of n plus 1 was half into xn plus 2 over xn, then we have to subtract xn. So if I put half and I multiply with xn, and then I still put a half and I multiply the half, I multiply with 2 over xn, the 2 just cancel and I get 1 over xn, then I subtract xn. So this gives me, I need to bring the like terms together. Half xn minus xn is simply minus half xn, then plus 1 divided by xn. So the LCM is just x of n, or basically 2 times x of n. Now here we are going to have negative x of n squared, okay, then plus 1, sorry, plus 2. That's what we have after finding the LCM. You realize that if I take this first term divided by this, I'm going to have this, and if I take 2 divided by 2xn, I get 1 over xn. So this simplifies to give us, we can write it as 1 over 2 times, I allow the xn here, I'm going to write it as 2 minus xn all squared. Okay, I'm going to write it that way. In fact, you realize that if we factorize a negative sign, then instead you are going to write xn squared minus 2. But now this resembles the derivative of our function. It's clear. The derivative of f was, this is a derivative, and we saw that that derivative was always positive, right? We saw that the derivative was always positive. And since this resembles a derivative, it means that, but now there's a negative sign. So we can just say, okay, this one is equal to negative f prime of x of n. Okay, now we know that our f prime of x of n was positive. So if we multiply both sides by the negative sign, it was greater or equal to 0 even. If we multiply both sides by negative, the inequality sign will reverse. So negative f prime of xn will now be negative. But negative f prime of x of n is simply our x of n plus 1 minus x of n, negative. So in conclusion, we can say that the sequence x of n is a decreasing sequence. So x of n is decreasing as required to show. Alright, now the last part of the equation is asking us to study the convergence of x of n. So you need to note that if a sequence is monotonic and bounded, then it converges. So we have to study the convergence of x of n. So we use the fact that x of n is monotonic. We saw it already, that is monotonic decreasing. We have just proven it. X of n is monotonic and bounded. We saw it already, is bounded between root 2 and 2. So x of n converges. That's a theorem. We just deduce from there, converges. Now it converges to its lower bound. Why the lower bound? Because it is monotonic decreasing. So it's going to be decreasing, okay, and it's converging. So it's converging to its lower bound, which is the square root of 2. But anyways, how do we get the limit? So since x of n is convergent, okay, then the limit as n tends to positive infinity of x of n plus 1 is the same as the limit as x tends to positive infinity of x of n. So this means that the limit as x tends to plus infinity, our x of n plus 1 was half into x of n plus 2 on x of n. This is going to give us is going to be equal to the limit as x tends to plus infinity of x of n. So we could factorize a half outside, and then we are left with x of n plus 2 on x of n equal to the same limit of x of n. Now if you call the limit L, right, if you call that limit L, it therefore means that we just have half into L plus 2 on L equal to L. If we multiply all through by L, we are going to get half into L squared plus 2 equal to L squared. Now if we now multiply all through by 2, we get L squared plus 2 equal to 2L squared. If you subtract L on both sides, L squared on both sides, we are going to have L squared to be equal to 2. So it therefore means that L is equal to plus or minus the square root of 2. But now, what do we know about the sequence? But since our x of n is a positive sequence, right, it's clearly a positive sequence since it's bounded between root 2 and 2. Since x of n is greater than 0, then the limit cannot be negative. Then L will also be greater than 0. So it therefore means that we need to take L to be equal to the square root of 2. And the square root of 2 is clearly the lower bound of the sequence x of n. So it ties with our conclusion that x of n is monotonic decreasing and lower bounded by root 2. So it converges to its lower bound. If it was monotonic increasing, it's going to converge to its upper bound. Alright, but anyways, it's not in all cases that it holds. Yes, it's not in all cases that it holds. That's why I tried now to use this other methodology to be very sure that the results are okay. Alright guys, so that brings us to the end of this video. Make sure you like, you share, you comment, and I wish you all the best for your continuous assessment evaluations.